Hi, this lesson is going to be on angular momentum, and it's a review of what we've covered during the year. Okay, so what I'm going to cover is rotational momentum and its conservation, and we'll talk briefly about experimental aspects of this towards the end of these, at the end of these slides. Okay, first off, objects that are rotating also have angular momentum. For a point mass, this angular momentum is calculated as simply the r vector, distance from the point of rotation, times its momentum vector. Okay, actually not times, cross product with its momentum vector p. Okay, so don't worry about the direction of the result here because we don't really need to go through the right-hand rule all the time. Focus on whether the object is rotating counterclockwise or clockwise with respect to that point of rotation. Okay, formula-wise, we're pretty much going to talk about it as simply the angular momentum vector L is going to be equal to r times p times the sine of theta. Usually that angle is going to be 90 degrees, but pay attention just in case. For solid objects, the angular momentum is going to be given by I omega, at least the magnitude of it. Again, if omega is counterclockwise, it's positive. If omega is clockwise, it'll be negative. Okay, so for point mass, I is going to equal mr squared, omega is v over r. When we do that, we find we end up with the same formula as above. Okay, so don't be afraid to be able to calculate angular momentums for a single point mass. Okay, so angular momentum, just like linear momentum, is going to be conserved. When objects collide, both of the angular momentum and linear momentum will be conserved in a closed system. I put those in capital letters because sometimes it's hard to see when a system is closed. I'll show that to you in examples 1 and 2 later on, but it's still going to be a Newton's third law rationale as to why the momentum is conserved. Okay, and again, just like with regular momentum, pay attention to the direction of rotation because it's a minus sign difference between clockwise and counterclockwise, and ends up being a lot of errors associated with that. Okay, so here's the first one. I have a rod of mass m and length l. It's at rest, and the rod is free to pivot about an axle on the upper point. Okay, and determine the angular velocity of the ball-rod combo immediately after impact. Okay, anytime you have two objects coming together, you should think of this as a conservation of momentum, either linear or rotational. Because it's got an axle, rotational's got to be involved here. Okay, so solution-wise, we can calculate the momentum of the ball right before, okay? It's MVL. MV is the momentum, L is how far it is from the pivot point. Okay, before impact, the rod's not moving, so its angular momentum is 0. And so my total angular momentum is simply MVL before the collision. After the collision, okay, I have no external forces. Yes, there's a force in the pivot, okay? The pivot acts as a force, but it doesn't act as a torque. The reason it doesn't act as a torque is because the R there is 0. Okay, so if I talk about it as a force times a radius, it's a 0 torque. Okay, so after impact, my angular momentum must also be MVL. Okay, so the moment of inertia for the rod, it's moving now. So the moment of inertia for the rod is 1/3 ml squared times omega, and the moment of inertia for the ball is ml squared. So if I add those things up and do it as a total moment of inertia times omega, I set that equal to MVL, I'll find that omega is equal to this formula. Okay, so here's a similar problem, except in this case I got rid of the axle. Okay, because I got rid of the axle, there's no external force from a linear perspective either. Okay, so in this case the ball's going to bounce backwards, the rod's going to keep moving at some v prime that we have to find. Okay, and so we have to find v prime and omega prime after it's hit. Okay, so because I have no external force in this case, I can do both linear momentum conservation and rotational momentum conservation. And when I do that, I find I end up with these answers here. Okay. Experimentally, we don't frequently see situations involving conservation of angular momentum. They're just not that common, but you can do it, okay? As long as when the object pivots around its center of mass, we can measure velocities and rotations before and after. And so it would be very similar to what we would do for a standard conservation of momentum. Okay, usually what we're trying to do here is to actually measure the object's moment of inertia, but it is possible to do. Okay, thank you.